All right. Hello, everyone. Let me turn this on so everyone can hear me. All right, that's on. All right. Welcome back. Today was your first homework was due today. So hopefully everybody submitted. For class participation submission deadline, we noticed, and also some of you brought this to our attention, my attention, that the class participation that are due on Friday, like they are given on Friday and due Sunday morning, Sunday night. Sometimes you forget about them because it's Sunday. So if they were supposed to be from now on, if they were supposed to be due on Sunday night, I'm gonna make it due before class time, like 3 p.m. on Monday. But don't expect all the class participation on Friday to be due on Monday, because if you notice, if a question is longer, needs more time, I usually put it for Friday, so you have the weekend to work on. So for those, if it was longer, it will be due on the Monday before class time. But if it was a small question or quiz, it's either gonna be due in class time or the night of that day that you had lecture. The idea is that I want you to at least review the lecture slides the day that you were taught, and hopefully some of that will remain with you and you will not forget for the next class, or at least you tested yourself. Oh, I didn't understand by just listening. Maybe I need to go back to it. Now you either do it right away or you put a star for yourself. I need to review this. And as you can see, a lot of the lectures that I designed, they are connected to each other. I do that on purpose. So you kind of built your knowledge. So if something you didn't learn on Monday, there was a class participation, you struggled or you got it wrong. And then when you're coming to Wednesday, you need to know you need to work on that topic. Otherwise, Wednesday class is going to be also difficult. There's always class participation, right? Well, most of the time. So you're gonna constantly evaluating yourself, and you might constantly get that, I don't understand, I don't understand, I don't understand. Well, part of learning is not understanding. What's the solution? Putting time to learn, right? Now, one of it is, I know that some student here, they have to go and read the textbook, watch the lecture, do the lecture themselves to actually learn things. That's your study time. Some of you can learn in the class because I provide enough, I think, at least fundamental examples that walks you through the basics of the method. Now, if it is more complicated, it will be your homework, right? So you actually have time to do that. So I'm providing a system that I think it works. Now, I don't know all of your systems, how you learn. You have to adjust to this method. Now, the other tool is office hours. Both of us go online on Zoom during our office hours and have in-person office hours. So use that time. So if you didn't understand something, simply come to office hours. Can you explain this again? Yes, I'm sitting there to help you. If the office hours doesn't work for you, email us. I can't make it to any of that. Can I come to your Zoom office in one of these days that works for you? So in your email, make sure that you put that. So I'm sure that I can find a time that works for both of us. All right. Don't leave it for, I will do this later. Later will never come. All right. Getting an A. I have students, they get an A from this class, but they actually don't know how to design a controller. So A does not mean you actually learned. It just means you did your assignments. At the moment you could solve it, 3 months later, you have no idea. My goal is for you to have an idea 1 semester after, at least, what you learned here, okay? That's why I really don't care about grades. If you be my student, you know that I really don't care about grades. But it is a motivation for you because you want your overall GPA to go up. So please use the office hours. Please use class time. When I give you class participation, just don't sit there, use your phone, because if you don't do it, then you cannot do your homework. Or you can, so we've been checking the last class participation state space system. I know most of you didn't know. I talked about it the first time, then the second time I brought an example. Still, when I say, do you have a question, you don't raise your hand because maybe you're intimidated. I created Discord. If you don't put there, if you don't give me feedback, the system is gonna have error. That's this course, right? You're the system. I'm that sensor. Like, this class is the system, sorry. You're the sensor. If you don't give me the right reading, I think I'm doing a great job. There's no error. I can't fix things. I have, like, as a teacher, I can come up with different method that would work for my students. But if I don't know, I think, yeah, go Dr. Z, you're the best. And what you're doing is working. It might work for 50% of you actually, but it might not work for the other 50. So my time outside of office is for that 50, or I can adjust things. Like I'm adjusting the CP if it's due on Sunday, it can be due on Monday. It makes your life easier and you don't get a 0. If I didn't have that feedback, it would keep happening. And a lot of good students would get 0. And I would be like, why are you getting a 0 on a simple assignment? Right? So please give feedback. Raise your hand in the classroom if you have questions, or if I ask someone, give an idea, talk about it. Now, I read the anonymous surveys, and I think 1 or 2 of the students, they mentioned they don't like to be picked on or called on, but it's an anonymous survey, so I don't know who you are. It doesn't work. But I get the idea. So I don't know who you are, but let's say David. I don't know if he likes or not. I'm calling his name. He can simply say, I don't know, right? This just means that he really doesn't know. Now, it is for you to evaluate yourself. You don't know because you're not paying attention. You don't know because you didn't learn it, or you were just zoned out. You didn't even hear what I said. There are 3 different I don't know. You can communicate that with me and I will repeat it. Don't worry. Like I've seen enough breaks in the lectures that even if I cancel Friday's class, we would not be behind. So we have time to discuss things in the classroom. This is a 3,000 level class. It's not a 5,000. I'm not expecting us to go really fast. You're on your own. You're actually not on you're on me. But if I see everyone is happy, keep looking at you, you say, yeah, I know. I ask a question, you keep answering. So I'm thinking, okay, this is a good example of the whole class. So let's go with your pace. You'll be happy, but a lot of you might not be happy because you were not the one that answered, right? So, but I don't have a good gauge because you might not answer because you're shy, you don't want to talk, you don't want to, I don't know, be embarrassed in front of classmates, which at this age, I don't know. Who cares about your classmates? I'm sorry, but you have to think about, you're paying money to be here, right? So you have to get something out of it. So long story short, ask for help, give me good feedback. If you don't understand something, raise your hand. It's fine. Worst case scenario, what I would say, I don't know. That would be my answer if I don't know something. I don't know everything. And I will go back, find an example and come here and explain it to you. So don't expect me to know everything. Obviously, I don't know everything, even in control that I think I know a lot of things. So CP6, is that what you're grading right now? So state space doesn't look very promising. So I will let you to grade and then find out what part was the problem. Was it the transfer function part? Was it the flow graph diagram? Was it the state space? We also look at the homework. If you're doing better in homework, it could just mean that it was too close to the lecture. You didn't have enough time to practice. After homework, if needed, I will create a review lecture, cover everything that you needed help on. So those are our tools to help the class learn the topics before we move forward. Everything is connected. I can't go forward if you don't understand or know a state space. It makes it really difficult because our next MATLAB class is converting a state space to transfer function to state space. So if you don't understand the concept, knowing the command doesn't work. You get an A, but you don't know what you did. Make sense? So we will revise after homework is graded. So I talked about the class participation also. Anything else that I missed? Okay. Good feedback. You're great, Dr. I mean, I love to hear I'm great or not any feedback, but I know it's not true. All right, so things that I have done here. Ooh, I published your homework too, since you're done with homework 1. You don't have class participation today because now you just submitted the homework 1, so I feel like you can take a break. but we're going to talk about mechanical system, which is important. I posted a solution for CP6, so go ahead and check to see if you were on the right track or not. Use the fishbowl for, I didn't understand the flow graph diagram. Can you solve another example? That I don't need who you are. I need to know who you are, so I can do that. Don't watch this yet. Force voltage analogy, that's going to be on Friday. Also, since I'm talking about Friday, tomorrow is supposed to be blizzard thing, right? I'm from UP. Blizzard in Columbus doesn't actually mean blizzard for me, but because our cars here is not proper for our road condition, even a thin layer of ice could be dangerous. So that's going to happen on Thursday. On Friday, if this continued and like it was really dangerous to come to campus, in the morning I will send an announcement if make the class on Zoom, so you don't have to come in person. But if no announcement, class is in person. All right. So if it was just snowing pretty, we'll come in here. We're not afraid of snow. But if it rained so bad or snowed so bad, I won't make you walk into it. But I will send an announcement in the morning. Cool? All right. Nothing against you, just you're my eyesight. All right. Today we have mechanical system, mechanical models. We talked about it, so hopefully it should be easier to follow. If it's not, let me know, because Friday we're going to talk about electromechanical system and then how they are related. I know that you, at least we talked about electrical system and you kind of are more familiar with that. This is the part that you might not be very familiar. So I brought a few examples. Now, when we talk about motion in mechanical system, we usually have two kinds of motion. Either they are translational or rotational. Now, do you remember the spring mass system that we discussed? That's a translational motion because your spring would move only in translational direction. Now, we also can call it a degree of freedom, or you can call it XYZ plane, like axes. So if it is on a flat surface, it only moves to the right and left. So along that axis, so 1 degree of freedom, if you want to say, or translation in that along that axis. Now, if it's inverted, it will go up and down, right? Usually, you don't have anything in between because it will just start going pendulum kind of thing, right? And then the motion will be combination of horizontal and vertical. So usually, why am I here? Nobody says anything. I was actually talking about that. So when we have translational, how do you know is it a translational motion? You observe. Oh, mass spring, and the spring is a linear spring, so this must be a translational motion. It is important because remember, we need to define our system, then you need to find the set of equation to use. Translational motion and rotational are different. So for translational motion, which was our previous example and you're familiar with, for spring force, we use F equal Kx. You remember when we move a mass, an object, if it's connected to a spring, what does the spring do if I move the object to the right? So wall, spring, object. Let's do this. If I pull this here to the right, what does the spring do? Okay. Opposes, right? So it wants to pull a force, exert a force on the system to avoid the motion, basically. But if our force is greater than Kx, the force applied by the spring, we actually can go to the right. If it's not, the object does not move. We usually consider the force we're applying is greater, so actually we're considering it moves. But I don't know if you ever pulled a very, like, a spring with a very high K and you couldn't actually pull it. I don't know if you had that experience. It's just because it's very, the spring is stronger than you. All right. So if this was a spring, would be F of X, F of K, let's say, I'm gonna Kx. So if this was K, so it would resist or oppose the motion opposite of the direction of your displacement. So what does that mean? We always have to assume a direction for the displacement, right? It's important because it would tell us which way the spring is actually exerting the force. It would be to oppose that motion. If we have a friction or if we have damper in our system, so damper or dashpot or friction, they act the same. If we have those, then the force opposes what? You remember? So it opposes the force applied, right? Yeah. Now, what is that force from a damper made of? There's always a coefficient, right? So think of the spring was opposing the displacement. What does a damper oppose to? We talked about it. I want to see if you remember. The speed, the velocity, right? So it is a force that opposes the applied force, but you can build it based on the velocity, how fast you are pulling. So if you mountain bike, I don't know if you did or not, if you push, you get the feedback. So the harder you push, the harder it sends through you. So you can jump on things easy, right? So if you do a little push, you're gonna go tumble down, nothing's gonna happen. Because the force is linear with the speed. So every time you have friction or dashpot damper, it is opposing the velocity or speed of the system. Which you can also say, right, B dx dt, if x is your displacement, right? So dx dt or x dot is your velocity. So if you remember this, you actually never need to remember the equation because you already know, you always would know how to create that force, right? Now, the other thing that will come into play is the inertia. What's the role of inertia? What does inertia do? Doesn't like change, right? Doesn't like anything that changes the state. And it is because of the mass of the system, right? So if I'm running, the inertia wants me to run. And if I'm not running, the inertia wants me not to run. So to run, you actually have to put a big force. Like think about when you're starting a task, it's very difficult because you're going from of not doing something to do something. So that's inertia. Same thing with the physical system. And the force is ma, mv dot, or mx double dot. They're all the same thing. They're just different way of saying it, right? So this is more of like a momentum kind of thing. This is more of mass time acceleration, but at the end of the day, they're the same. You can also write them as dx dt squared. So you can see the differential equations, right? So a system that has mass, spring, and damper will have all three of these elements in there. If it's missing one of them, it's going to miss one. Now, out of these three, which one you think a system will always have if there's a physical system? Which of these three forces we cannot live without? Did I say right? We can't live without. Inertia. So spring might not be there, damper might not be there, but the mass has to be there because there is a physical system. So you always have m multiply x double dot. Your acceleration could be 0. I could just be here and not move, right? But mx double dot is here, x double is just 0. But there's no k connect, like there's no spring connected to me. There is a friction, but let's say there was no friction. We could have dx dot also be 0. These are important because there are two ways. Sometimes you have a system, you see mass spring and dashpot or friction and you model a system. Sometimes you get an equation and you think what kind of system this could be. Then you say there must, if you had some term k times x, you say that there must be something in terms of elasticity because this have that kind of force in it. If it has like b x dot, there should be something like friction. Now, what does friction do? opposes, and also in terms of energy conservation, what does it do? Yeah, it changes from one type like to other, like heat, right? It wastes energy usually, friction. Dashpot also usually wastes energy, right? It slows down. So moving from kinetic to potential energy or something like that. So whenever you have like a B X dot term, the energy is being converted, but it's being wasted in the system. Now, what does KX do? Your spring. Restore the energy, because if you push the spring, what happens if you let it go? Toss back. So the energy didn't go anywhere. It's just restored. Now, it should have sparked some ideas thinking of electrical components for you. So if I give you an equation that has X dot in it and X in it, you should think of wherever I see X with some coefficient, there is some restoring element in there. Could be mechanical, could be electrical, could be hydraulic. Whenever I have something times X dot, I'm wasting energy here, right? So like resistors in your electrical system is wasting, so you would expect you have a resistor if you have that, right? It's similar. So you could get an equation and then you could define two different systems, mechanical or electrical. You just have to pick different components. But if you don't know what's the nature of that force or what you're seeing, you're not able to do that. After this course, I want you to be able to look at a differential equation and tell me if this was a system, what could it be if it was a mechanical system, or what could it be if it was electrical system? All right, and they're analogous. Like you just need to pick the right component, and then that's it. All right, we will do that on Friday. I think that's a great connection between electrical engineering and mechanical engineering, and why we have so many electromechanical systems. Yes. Represent what? Like building. Maybe, I don't know. I can't think of an example. Can you give me an example?
The system is time dependent, so like, I don't know, I'm just thinking this off like.
We can check that, because so there are different applications. So if you think of in terms of hydraulic, then it's the velocity of the flow, like it's the flow rate, right?
That's like more like, say some input is coming in, but like.
Oh, you're talking about like just a rate of change of something?
Even if you make it, can I give like a very structured example? So like say you have 3 apples coming into the system, I'm going very, very like, basic. And you said something, you get washed, but say the apple, some of the apples go to the output where it gets checked, but some of the apples go back to the original like input to, I don't know, add on, so like feedback, but wouldn't that just be like delay? Would that be the delay?
It's not the delay. No, I don't see that as delay.
Okay.
No. Delay, you can see the delta T, delta X, right? So delay is because of so you're in time domain, or you could be in frequency domain. So that's that phase shift, that delta theta or delta phi, that is the time shift, phase shift or time shift. So we can define delay depending on what time domain we are at as that extra delta. Here is our system. We are defining system. Actually, that's a good reminder in your homework. Question 1, like some of you came to office hour, we discussed. I'll discuss this when I post the solution, but every system you have to first look what time domain I'm in, right? So all of those were what domain you are, sorry. You could be in time domain, frequency domain, S domain. All of those examples were in time domain, right? So time is shared between all of them. So if I didn't give you time, you should have been fine everywhere except wherever you had input. Because input is from the domain you are, is not part of your system. So I can have my system and put it in different domains, and it should be the same thing. So if I remove T, it should still make sense. But if it's an input, then if I'm in time domain, like sine of t, if I take the t out, sine of doesn't mean anything anymore. So that's the input of your system in time domain, right? So it is important that you understand what your system is. Now, delay is because of the domain you are. So it's a function of time, right? What your domain is running on. I'm late, delta theta, delta t, because I'm living in time domain. If you were a sine function, your delay would be phi, which is a phase shift, is in terms of frequency, right? So this is a like we kind of veered off, but I think like that related to question one of the example. So x dot is not a delay, but you can think of it as rate of change of something. All right. So flow rate is going to be x dot times some coefficient. All right. So these three are the forces related to translational motion. Now, if you have rotational motion, you're going to have, again, another three. You always will have inertia if you have mass, right? Now, the inertia in rotational motion doesn't depend on your acceleration anymore. It does kind of depend on acceleration, but not acceleration of a what do they call it? Translational motion. In rotational motion, what is your displacement? So let's say you have a wheel, right? It's in a rotational motion. Start at time at home, 0. And some time passes. I want to see the displacement or the rotation in this. What would that be like in this example? An angle, right? So displacement in rotational motion is angle. So I could go here, theta. So everything else will remain the same. So the forces will still exist, but instead of having force, you have torque or moment. Your displacement instead of x is theta. Now, if you have a spring, you just simply multiply k times your theta instead of x, because x doesn't exist anymore. Now you might say, well, if you have a wheel, car actually goes forward. How do you explain that? What are you actually doing? Whatever, you're converting your rotational motion to your translational motion, right? So don't get them confused. If something is rotating, but you see a linear motion happening, it's not that that was not a rotational motion. There is a mapping conversion happening here. Linear actuator, the best example. It rotates, it has a DC motor, but it pulls a pin, like you can actually go on an axis. It's called linear actuator because that conversion is happening inside of it. All right. So the system is the rotational. All the equation will be written in theta. But then we have to do a conversion to make it a translational motion. So for rotational motion, we use those equations. And k theta, b theta dot, and then for tau, you use J or sometimes use I. That's the inertia, moment of inertia for that object. That's the only difference. There are still the same three forces that exist, the same nature that we discussed on the first one. It exists on the second one as well. In my annotated version, I wrote it cleanly, so I have all of them, but the gist of it is basically the three forces and torques are kind of similar in nature. Now, when we are in translational, we write sigma F equal to MA, right? So don't forget, this is that mass and inertia. So we can say addition of all the forces are equal to the inertia of the system, or M times A, which A is X double dot. And then for here, sigma M or tau, I'm going to write tau, but also M is the same thing, is I times alpha. Now this is angular acceleration. If this was linear acceleration. my acceleration is wrong. There's two C's. So you see that so if this was mass, this becomes inertia. So if you identify this is a translational motion, this system has translational motion, you use those three equations plus sigma f is equal to ma. If it was rotational, you use this set of equation. All right, now solve this. Write the equation of motion for the system. First, what kind of a system it is, then try to see if you can write the equations. So what kind of motion do we have? Translational, because I said on top right there. Because it's just moving in a translational direction, right? It's just going down. Now, there are a few things. First, identify your mass. The thing that will have the inertia, right? How many mass do we have here? One. So I'm gonna call this M. So this is how you do free body diagram. If you skip this steps and just write the equation, I'm not gonna give you the whole point because you need to show your work. So I need to know you understood what you did, because you can actually memorize all of this. I don't want you to do that. I want you to be able to do the steps. So translation of motion, I know I'm using sigma f equal to ma. I'm gonna draw free body diagram. So inertia, like mass represent inertia, I'm gonna have that. I have F, that is an external force pointing downward. I've also been told this is the direction of the displacement. I need to know that so I can say the opposing forces will go the opposite side, right? Point upward. What are the opposite forces, opposing forces? This one, Kx, so F of x is Kx. And this one, F of B is Bx dot, right? Where is inertia? What does inertia point? Where does inertia point to? You're pulling it down from not moving. So from home position, right? I want to pull it down. Inertia doesn't like to go down, right? It will oppose. So your inertia will be here. So it doesn't apply on the mass, it is the mass. The mass doesn't want to move. So that's why I personally draw it on the side. So I know this is inertia because of the mass. So it's mx double dot. Now you have all of your forces. You can just say that external forces are equal to internal forces, but this is also the same thing. So you could say that, you know what, I'm not going to use sigma F is equal to MA. I'm going to say sigma F is equal to 0. The addition of all the forces is 0. So inertia becomes a force. So you can say that the direction of force is down. So this F is positive, negative mx double dot, negative bx dot, negative kx equal to 0. I'm following this. If I was going to follow sigma F equal to MA, I would say F minus bx dot minus kx is mx double dot. It's the same thing. We just move it to the other side. Use whichever makes more sense to you. I usually use this one because for me it's easier to remember. But you can do either one. At the end, we'll have the same thing. So I have that. I'm going to rearrange because this F is your input, right? We like to keep the input on one side, everything else, the system on the other side. So mx double dot plus bx dot plus kx equal to F. You could also write mx dt2 plus b dx dt plus kx equal to F. So this is differential equation of the system. And you see that it looks like your other system you had before, right? Because we are dealing with the spring mass system. Now, one thing I assume, but I didn't talk about it and didn't write it. I actually talked about it, but I didn't write anything. I said this starts from home position, meaning that it when you connected this weight to this spring, it actually spring went down and it was not moving. That's why I don't count mg. But if I said that just this is your spring and dashpot, write the equation from when you put the mass, then you have to count mg because mg is going to pull the spring. So this is after the spring was pulled. So this is at x equal to 0. This is really important. That was my assumption, that this is after natural position. All right. If it wasn't, then you had to have mg. On the flat surface, you don't have mg applied because it applied everywhere. That's why the equations look the same and you don't have the gravity. Make sense? All right. Sometime we could have multi-mass system. You solve this one. It's the same thing, you just have two masses. The only thing you need to pay attention to is if we have two masses, there will be an interaction between the two, right? Then we need to count those. Actually, I'm going to do it and I'm going to do it faster, but I want you to all pay attention and you can take note as I do it. So we have two masses, so I'm going to have two free body diagram. Is this a translational motion or angular motion? Translational. So I know I'm using sigma F equal to 0 or MA. So I'm going to have free body diagram for mass 1. This is very important. So you want to pay attention to this for mass 2. So I kind of I'm cutting things. Isolate the mass for free body diagram and see what are the forces applied. So I know this is the direction of F. I'm going to say x2 is going to be in this direction. x1 is going to be in this direction. I decided. It wasn't given, but you have to put that first before writing your equations. Now, this is F. I'm just going to put x2 here so I remember. Now, I know my inertia is going to be in this direction, right? What other forces do I have on mass 1? What other forces we can see that, what other elements have impacts? So the first is spring, right? K1. So K1 also doesn't want this to move, so K1. But we should, the force is K times displacement, right? Now, the thing is we have two things, two masses that don't also have the same mass. M1 and M2 are not equal. So we need to count the interaction between them. So I'm not gonna write what, I don't know what displacement is gonna look like. I'm gonna keep it open, so we will see once we do the other side. Now, if you have one object and apply force, is connected to the other object, how does this force looks like on that other object? So I'm pulling these two apart. One force is pulling this way. What's the other force gonna look like? Equal and opposite, right? So I start from here, K1. That's the first thing I'm gonna do. Equal and opposite. Then K is times displacement, right? The displacement is going to be, so if both of them, so I said x1 and x2 are going the same direction, what's their relative? How do I write their relative displacement? x2 minus x1, for example, right? So I'm gonna write this, but keep it the same for both. And it really doesn't matter if it's x1 minus x2 or x2 minus x1, as long as they are the same, because there are two forces equal in the other direction, opposite direction. Now, at the end, once you solve, you will have that, you might have a negative value for one of your x. It just means that the direction was wrong. That's all it means. So if you go with your own assumption, you will be fine completing this example. So I took care of that K. Now, what else do I have? So I know the direction of x1 is here. So m1, x1 double dot, opposite direction. B x1 dot and k x1. You have free body diagram. From here is a downhill. You just have to write the sigma f equal to 0 or equal to n, depending on how you look at it. So for m1, mx double dot 1 minus k x1 bx dot 1 plus k x2 minus x1 equal to 0. You can rearrange. It will be mx double dot 1 plus bx dot 1 plus, I'm just going to put the k's so I have something times x, so I would know, minus k x2 equal to 0. For m2, same thing, just have more forces, well, less forces, f minus mx dot 2 minus k x2 minus x1 equal to 0. If I rearrange, I have m2 x double dot 2 plus k x2 minus k x1 equal to f. So I wrote differential equation for both of them. I have two mass in my system. I expect two second order differential equation. I got that. So this is in time domain, right? If I wanted to represent this in state space, I could have done that. We actually will do it, but not right now. I want to make sure like where we are on the state space, I might need to do a review. But you need to take it, yes. What, which one? This one? This is not a dot, this is a 0. So sigma f equal to 0. Yeah. So that is a system of equation you have. We can convert it to state space representation. And then from there, we will do our control, which we haven't got there. You always have to create your system first and put it in one of the representations. Yes.
So why do you not use the F on the M1?
Yeah, it's not connected to it. So I'm actually, so let's do this. Come here. Can you see the, say, I had another case to do in this way. I'm gonna hold it here. Behind, turn around. Okay, come pull him. Okay, pull him. So if he doesn't move, I won't move, right? But if he moves, then the second mass moves.
Okay.
So the force, thank you. The force is applied on the first one. It has to first move that to be able to move that, right? You'll see something like this in your homework also. It's follow the same lead and you can do it. What if we have rotational motion? It's the same thing, you just have all the taus. Free body diagram. How many mass I have here? How many equations do you think I will have at the end? 2. I have 2 masses, I'm gonna have 2 equations. Here, mass number 1, J1, mass number 2, J2. Let's identify the forces, well, torques here on the first one, right? I know I have tau A. Now, I don't have the direction of the displacement. Displacement is angular, right? I can assume a direction. So I put my assumption first. I'm gonna say this is my positive, I'm gonna call this theta 1, theta 2. Again, assumption, you could get it either way. At the end, if you found a negative value, it just means that your direction was wrong, which is fine. Like negative displacement means something. Now, what are the forces, what are the torques, sorry, applied on the first one? So, well, let's read. So we have, this is a flywheel. We have a KR here, which is a flexible shaft. Then we have to connect to unmoving wall. We have tau A, a torque on this. And then between flywheel 1 and 2, we have a friction, BR1. Between flywheel 2 and the ground, we have a friction of BR2. So now your dashpot could be a friction, you just model like as a dashpot, it doesn't matter. So let's just start with the second one. Well, we start with the first one, tau A, and then what is the other force that you have because of this spring? This is a torsional spring. What's the equation for force that is opposing the rotation here? What would be the direction? Opposing, right? So KR theta 1, opposing direction, and we know what the equation is. What else? We know we have inertia, right? Is going to oppose. So it would be momentum here. J1 theta double dot 1, and this is dot. What else do we have? There is a friction between these two modeled as a damper, but it's a friction. Again, we have another friction, BR, but what is the displacement here? Because it's between two objects, right? It's gonna have some impact on the other one. So we're gonna do the same thing. The direction would be opposite of the displacement. So I'm gonna write BR1. I know immediately there's gonna be the same torque applied because of that, opposite direction, BR1 times displacement. So I look at my displacement, theta 1 and theta 2. I know the displacement between them is theta 1 minus theta 2 or theta 2 minus theta 1. Again, doesn't matter as long as you keep those the same. So I think I wrote theta 1 minus theta dot 1 minus theta dot 2. Sorry, for this is not a displacement, is a velocity. Theta dot 2 because it's a friction. Theta dot 1 minus theta dot 2. Do I have anything else left on the first object? I've seen all of it, right? So let's go to the second object. I already have the effect of BR1. Now I also have a friction here that's going to also oppose the movement. So it's going to be BR2 times theta dot 2 because this is opposing the velocity or speed. Then I also have the momentum inertia here that will also oppose the motion. So J2 theta double dot 2. That's all of it. All you have to do now, right? Sigma tau equal to 0, sigma m equal to 0. They're all the same thing. Sigma tau equal to I alpha. So here our I is J, our alpha, or theta double dots. Or write sigma m equal to J theta double dot. All these four are the same thing. All you have to do is just write this equation. You'll get two equations for two mass, two objects you have. So this is a multiple system. We usually have multi-mass system, right? Most of the time. So we ran out of time. Well, we ran out of time. I wrote the equation in the annotated version. So you just simply put them next to each other. Don't have class participation for today. Review this for Friday, because we're going to combine this with the electrical system. It might be a lot because you're not familiar with mechanical system, but review them. All right. Thank you.